All right, welcome to Energy Podcast Part 2. In the previous podcast, we left off with a discussion of potential energy, which is how much potential something has to do work, such as a boulder lifted up to a cliff or a ledge. The higher it's lifted, the greater potential energy it has. Now, in the case of kinetic energy, that is the energy of something that is in motion. Kinetic energy is also known as energy of motion, and is expressed mathematically as 1/2 the object's mass multiplied by its velocity squared. And the beauty of this is this formula does not come from thin air. It is derived from other formulas, mainly the formula that we learned in Newton's second law, force equals mass times acceleration. For an explanation of how this is derived, you can see it's in one of the Hewitt-Druitt videos that are also attached to this page, or just come in and ask your teacher. He would love to show you how this formula is derived. For right now, though, what you need to know is that the kinetic energy contained in something is equal to 1/2 its mass multiplied by its velocity squared. And what this means is, if something is rolling along, it has a certain amount of kinetic energy. If the mass of the object is doubled, then you end up with 1/2 of twice mv squared, which is going to double the total kinetic energy. However, if the speed is doubled, 1/2 m twice the velocity, that's no longer just going to double the total energy. What that's going to do is that's going to cause the total amount of energy to quadruple because it's going up by the square of the velocity. So if you double the velocity, then it goes up 4 times. If you were to triple the velocity, then the total energy would go up 9 times. And that is how we use math to explain the amount of energy something has. The kinetic energy of an object equals 1/2 its mass times velocity squared. Now, the math that we use to derive this formula, it also shows us that the kinetic energy something has is equal to the work done on the object. So the force times the distance, which is work, equals the total kinetic energy of the object the work was done on, the net work. This is also where we get the work energy theorem, which states that the work, the force times the distance, is equal to delta, the change in the kinetic energy of an object. So the amount of work done equals the change in the kinetic energy. In order to have a change of energy, you have to have work done on it. What this formula also lets you know is, in the case that you have something that's moving that you want to bring to a stop, the change in kinetic energy is going to be equal to 1/2 its mass times velocity squared, the difference between that and 0. So the work done is equal to the change in the energy to bring it from a certain energy state to 0. So let's say you have something with kinetic energy of 500 joules of kinetic energy, and you need to bring that object to a stop. Then you're going to have to do the amount of work equal to 500 joules of energy to bring that to a stop. More on that in a bit. Kinetic energy often appears hidden. Kinetic energy can take the form of heat, sound, light, or electricity. Heat, sound, light, or electricity. In the case of heat, that energy results into random motion of electrons, which is what heat is. In the case of sound, the energy is transferred into a more organized motion of electrons that transfer a wave through a medium called sound. In the case of light and electricity, the energy is transferred into motion of electrons and atoms, which is where light and electricity ultimately come from. In the case of this bike coming to a stop, the energy that is associated with the rotating tire, its mass times 1/2 its mass times velocity squared, it doesn't disappear. That energy turns into heat in the tire and on the surface of the road to bring that bike to a stop. So the energy is still there, but instead of being the rotating kinetic energy of the wheel, it is now heat energy and some sound energy. All right, the interesting thing about this formula for kinetic energy being 1/2 mv squared is if the velocity of something goes up, the total amount of energy goes up exponentially. What this means is a car traveling 45 kilometers an hour that might have a typical stopping distance of 10 meters if you're slammed on the brakes, it has anti-lock brakes and everything's in working condition, it would take about 10 meters to come to a stop. If you were going 90 kilometers an hour and you slammed on the brakes, it wouldn't just slide twice the distance, it would slide 4 times the distance. If you were going 180 kilometers, then you would be having a skid of about 160 meters if you slammed on the brakes, 4 times what you would have at 90 and 16 times what you would have at 45. And if you look at this, 90 is twice 45. You double the V, the total energy goes up 4 times. 180 is 4 times 45. So if you bring the velocity up by a factor of 4, then the total amount of energy goes up by 16 exponentially. Now this has real life implications. Let's say that there's a wreck and there's some skid marks showing somebody slammed on the brakes that are 40 meters long. And the person is claiming that they were only driving about 45 kilometers an hour. Well, those skid marks show that for a typical car with anti-lock brakes and everything in working condition, that would indicate the car was going somewhere around 90 kilometers an hour, not 45. So the police and investigators can look at the length of the skid marks and estimate how fast the car was traveling when the brakes were applied. Because they paid attention in the physics class, learned a little bit about kinetic energy, and there you have it. Alright, so here's a lady with a bow, and she's pulling it back, and she's going to launch the arrow. Now, right now, when she has it pulled back, there is stored energy. This bow and arrow has the potential to do work now. There is stored elastic potential energy in that bow when she has it pulled back. If she releases it, that potential energy actually starts doing work while it's moving the arrow. That potential energy is turned into kinetic energy. But then, if you were to measure how much energy is actually delivered from that arrow to the target, it would be slightly less than the amount of energy in the bow and arrow. So what happened to the other energy? The rest of the energy. Now, the law of conservation of energy says that energy had to go somewhere. So the arrow hits the target. If you could somehow measure how much energy the arrow delivers to the target, it would not equal the amount of potential energy right now when this lady's holding it back. The reason is, some of that energy is going to be transferred into sound and heat as it hits the target, as it flies through the air. There's going to be some sound, which is a form of energy, and heat, which is a form of energy. If you take the sound and the heat and the kinetic energy upon impact, everything will add up to the total amount of energy that was contained in that bow when she pulled it back. Energy, just like momentum, is conserved. Here's another way of looking at it. Here's a little wind-up car. Had elastic potential energy in that coil when it was wound up. The coil is unwound, the car starts moving. If it started with 10 joules of potential energy, there still has to be 10 joules of potential energy somewhere. Although here, there's 8 joules of kinetic energy in the car, 2 joules were given off as heat between the axles and axle housings and between the wheels and the ground. But if you add up the total amount of energy here, it equals the total amount of energy started. And energy is conserved. Energy cannot be created or destroyed. It just can be converted to one form or another. Here's an example of a pendulum. If you pull the pendulum bob back and hold it, it has potential energy. As you let it go, it loses potential energy, gains kinetic energy. At the very bottom of its path, it's all kinetic energy. Then it goes back to the other side, ends up with some potential energy. If there were no friction, this would just keep going back and forth. It would gain kinetic, lose potential, then lose kinetic, gain potential. In the real world, there's friction, so as this is happening, back and forth and back and forth, the energy is constantly being converted into heat, and eventually this thing will come to a stop. Now here's a woman leaping from a burning building, and she's jumping. And while she jumps, she's thinking about her physics class and her potential energy and kinetic energy. And she thinks to herself, okay, let's say she has 10,000 joules of energy. That's potential energy at the top of the jump. She jumps. Now, if you look here, she starts out with 10,000 joules of potential energy. As she jumps, she's losing potential energy, but gaining kinetic energy. The whole time, the sum of the potential plus the kinetic is going to equal 10,000 joules. Halfway down, she's lost half her potential and gained it in kinetic energy. As she approaches the bottom, right as she hits, she's got 0 potential energy compared to relative to the ground, and 10,000 joules of kinetic energy is what she has now. All the while, up and down this whole trip, her total energy was 10,000. It was just transferred from potential to kinetic. Now, since we're on the subject of energy, we're going to talk about machines. What a machine is a device that can do one of two things. It can change the amount of force needed to do something, or it can change the direction of something. What a machine cannot do is multiply the energy. It can multiply the force. It can change the direction. A machine cannot multiply energy. That's a no-no in the law of conservation of energy. So let's look a little bit about machines. Look at machines a little bit here. Now, on the topic of machines and conservation of energy. In physics, in science, and nature in general, there is no free lunch. You cannot get something for nothing. You cannot get more energy out than you put in. You can manipulate the amount of force and the distance the force is applied for, which we're going to look at in the next couple slides, but the total energy in is always going to equal the total energy out. You cannot create energy. You cannot destroy energy. Machines cannot create or destroy energy. Machines cannot put out more energy than they put in. What machines can do is transfer energy from one place to another and transform energy from one form to another, but they cannot create or destroy energy or put out more energy than they take in. As you will see in the next couple slides, when we look at some simple machines such as a lever, it is basically taking a force times the distance put in and rearranging that force and the distance. It might decrease the force and increase the distance, or increase the force and decrease the distance. But the force times the distance in always equals the force times the distance going out. The work in equals the work out. Here is a very simple case of a machine, a lever, a seesaw. It is a plane, a board, pivoting on a fulcrum. And here you've got the input. If you take the force times the distance in, it's going to equal the force times the distance out. What's going on here, though, you're moving a much bigger distance over on this side, which is causing this side to move upwards with a much greater force over a smaller distance. This would allow you to lift something that was a lot heavier, but it would only lift at a small distance, but you wouldn't have to put in as much force. The amount of force put in is about half of the amount of force put out. But you can't get something for nothing. That is, the sacrifice here is you're moving a greater distance. You're getting a greater force output, but a shorter distance output. And you're putting less force in, but the trade-off is you're having to move at a greater distance. This is the principle behind a lot of jacks, hoists, and stuff that is used to lift objects that would otherwise be too heavy to lift on their own. You can use a lever to manipulate the force and the distance, but the work in still equals the work out. In the case here, you have a girl who is able to move this boulder, which is 80 newtons, by only applying 10 newtons of force. The reason she's able to do that is she's moving that 10 newtons of force a distance of 1 meter. The trade-off here is that 80 Newton boulder is only going to move 1/8 of a meter. And if you multiply 80 by 1/8, you get 10. If you multiply 10 by 1 meter, you get 10. The work in equals the work out. She's manipulating the force and distance, applying a small force over a big distance over here to get a great force by a small distance over here. That's a machine.